So we'll start again here. Try not to belabor anything here too long, because if I spend too long on any one item here, all of a sudden we'll be behind again. Sort of already behind. But it's just in my mind, don't worry. So here's the theorem. That, take off this stupid mask. Here we go. Alpha be unit speed, nonlinear curve. Then alpha is planar if and only if the torsion of the curve is 0. So here's the proof. In the forward direction here. So suppose it's planar. All right. Then alpha from I to R3 falls in plane with normal V. All right. So, I mean, here's a picture. There's some plane, right? And it's planar, whatever. There's a picture of alpha, and V is the normal to the plane, right? So what you do is you pick a point, S naught, an element of I, right? And that gives you alpha of S naught, a point on the plane, right? And then you can let gamma of S equal to alpha of S minus alpha of S naught. Right? So that's going to be a displacement vector. If this is alpha of S over here, right? Gamma of S is where it connects these 2 points, right? But, of course, we have what? Gamma of S dot V is equal to 0 for all S in I. By assumption that the curve is planar, right? If the curve is planar, that means that any point which connects that given point on the curve to another point on the curve, that vector has to be perpendicular to the normal to the plane. So the dot product with that has to be 0, right? Okay, so then you can differentiate this, and what happens? You get gamma prime of S dot V, which is, by the way, T of S dot V equals to 0 for all S. Right? But what else? Well, we can also differentiate that. Differentiate again. T prime dot V, which is, by the way, what? Kappa n dot V is likewise equal to 0, right? So I'm differentiating this right here. That's why I know that this is 0 here, all right? And then I'm using the Frenet-Serret equation to trade my T prime for kappa n, right? So what's this tell me? This shows me that n dot v equals to 0, right? let's summarize what we know. We know that v dot n is equal to 0, and we know what? T dot v is equal to 0. So what does this say about v? What direction does v have to go in? Right, I mean, right? I mean, if v is perpendicular to both n and t, and b is, and v is non-zero, it must be that v lies in the b direction. I mean, if you don't, I mean, you can expand v as what? V dot t plus v dot n plus v dot b at each s, right? And what's that? Exactly, 0, 0, and, well, this doesn't have to be 1, but it has to be like some constant k times b. But that k can't change from point to point, right? The length of v is fixed. Whatever it is, it is. So if k works out to be 2 at one point in S, it has to be 2 everywhere. K cannot be a function of S because v is a fixed normal to a given plane. This is important because then when we differentiate, and of course we can solve this, b is 1 over k times v, right? So what's b prime equal to? 0. Because it's equal to a constant vector, right? What does that say about the torsion? That says that the torsion is 0 because the torsion is equal to dB. It's, you know, torsion, b prime is torsion times n, right? So minus torsion times n. Since n is non-zero, it must be that tau is 0. So that's the forward direction of the proof. Now, what's the converse direction to the proof, right? So suppose, or assume, the torsion is equal to 0, right? Assume the torsion is equal to 0, and for all s and I, so I guess tau of s technically, for all s and I, and all right, so then b prime of s is equal to minus tau of s n equal to 0. So thus dB ds is equal to 0 for all s, right? Thus b of s is equal to, let's say, b sub naught, which is maybe, you know, like b of s naught. Fix a particular, b is constant since its derivative is 0 everywhere, right? The binormal has to be constant for the curve. And of course, we're going to claim that that serves as the normal for the plane in which the curve lies. So then O'Neill says, well, let's define a function which is identically 0 if the curve lies in the plane with point alpha of s naught and normal b of s naught. So following O'Neill, I will let us consider f of s equal to alpha of s minus alpha of s naught dot b of s naught. If I can show that that's identical, if I can show that that function's identically 0, that proves that the curve is planar, because it shows that any 2 points connecting, any 2 points in the curve, if you look at the displacement vector connecting those, the displacement vector is perpendicular to the fixed vector, which I'm claiming is the normal to the plane. So that is a vector theoretic way of characterizing planarity of a curve. And so we'd like to show that this is function's identically 0, and the way you do that with calculus is to take the derivative and show the derivative 0. If the derivative is 0, then the function's constant. If that constant's 0, we're done. So df/ds, well, what's that? That is alpha prime of s dot b of s naught, right? I mean, that's what it is. When you differentiate that, that's what you get, because, you know, alpha of s naught is a constant. B of s naught is a constant, so when you differentiate, that's what you get. But that's exactly t. Yeah, that's t of s dot b of s naught. Yeah, that's, how do we know? Yeah, how do we know that that's 0? Maybe I'm...
If it's in the same direction as B, it has to be 0.
Oh. Yes, but how do I... Well, yes, but how do I... I'm comparing s and s naught. What do I know about b, though? B of s naught is equal to what? B is constant, right?
So, yeah.
So whatever s I'm looking at, I can erase the... This is just the same as b of s.
Yeah.
Now that I'm comparing them at the same arc length, then I know that the dot product's 0. And that's true for all s, right? So how do you... So f is constant. Constant on I. And then how do I get its value? What point would you plug in to see what f is? How about f of s naught? What's that give you? Well, plug in the formula up here. See what happens when we plug in s naught? We get alpha of s naught minus alpha of s naught, which is 0. So this is 0. Thus, the function f is identically 0. Therefore, the curve is planar. Trust me when I tell you that the proof that you're looking at, and this proof is largely from O'Neill, this is a very nicely done proof. I have tried to prove this in the wild, left to my own devices, and I have found ways to make this much, much more difficult. Like, this is not an easy thing to prove if you just attack it directly. The next about page and a half in my notes is devoted to looking at the Taylor expansion of a curve into arc length and how the different coefficients in the Taylor expansion relate to curvature and torsion. And that's interesting, but I'm going to skip it. The next theorem is as follows. Again, alpha, just like before, nonlinear unit speed. And this one with curvature kappa of s equal to a constant, kappa sub naught, which is not equal to 0. And we also are given that the torsion is equal to 0 along the curve for all s in the domain I. Then alpha of s follows a circle. Radius r. 1 over the curvature. And so in my notes, I just tried to write a proof down according to my natural tendencies. And about after a page, I reduced it to 2 third-order differential equations whose solution parameterizes a circle. And I left that proof there because it's mine, but it's not a good proof. A good proof is proof 2, which is from O'Neill. Here it is. So his proof is much easier. He says, assume alpha is unit speed, nonlinear, constant curvature, torsion 0, and consider any point along the curve, all right? The normal vector should point towards the center of the conjectured circle, right? So if we think about, if we believe what we're proving, if this is alpha, right, then there's supposedly a center of the circle in here, right? And we should be able to write, gamma of s equal to, come on, where'd you go? Alpha of s plus r times n of s. Let me try that. 1 second here. So this point here would be alpha of s. N of s should be like this, right? And so this point C down, let me erase this for a second. That point C down there, to get from here to there, I should have C is equal to like alpha of s minus the radius multiple of n at s. Like if the radius was 5, I would need to subtract 5 normal vectors to get from a point on the outside of the circle to the center of the circle, right? We're not assuming what we're trying to prove yet. I'm just trying to explain to you what we're looking for, all right? And of course, we're going to set that r equal to 1 over kappa. All right, so with this in mind, we let gamma of s equal to alpha of s plus r times n of s, right? The reason we do that is that should do what? Oh, I think maybe I have a, I think I've got a typo right there, actually. I think it's supposed to be a minus. I talked myself into this being a plus earlier, but I actually think that's supposed to be a minus. Because if I could show that this path was actually not an honest path, but a point path, if I could show that that was identically 0, that would prove that that C was a fixed point. And then I could probably prove it's on a circle. All right, so let's try to do that. So put a minus there. I think my notes have a typo right there. Differentiate, what do we get? We get alpha prime of s, right? Minus r n prime. But what's n prime equal to? N prime is equal to what? So what we're looking at here is t minus r times, what was n prime? It's minus kappa, which is kappa naught t, right? Plus the torsion, which is 0 times b, using the Frenet-Serret equation, the second Frenet-Serret equation right there, right? So what happens with that r and that kappa naught? What happens with that r and that kappa naught now? So, I mean, these guys cancel. Minus minus gives me plus. Oh man. What? No, I need a plus there. Oh, I'm an idiot. This should be plus, right? Geometrically, if I'm going from here to there, I need to add copies of n to get to the center, right? You guys, don't let me bully you into this nonsensical statement I made earlier. That's a plus. And so should this be a plus, which is good because then this gives us t minus t, which is 0, which is good. So this is 0, which means that the curve gamma is identically 0. Well, it's not, gamma's constant, right? So let C equal to gamma of S naught, right? Well, that's equal to gamma of S for all S in I, because gamma is the derivative of gamma is 0, right? So whatever it is at S naught, it stays that. We might as well call that point C to connect with my discussion, right? That doesn't yet show it's on a circle, right? What do we need to do to show it's on a circle? To show that alpha is on a circle, what we should show is that the distance from alpha to C is fixed, right? So we should look at the length of, alpha of S minus, C, right? Squared. We'd like to show that that's a constant. And that we'd like to show that that constant's equal to r squared, right? Now, this is actually, alpha of S. Yes. So that's actually alpha of S minus what? C was equal to what? It was equal to alpha prime of S plus r n prime. Oh, I'm sorry. I seem to have, I'm mixing my derivatives and my other formulas. I got to be careful here. So it's supposed to be alpha of S minus C. I'm too close to the board. Let's see here. Okay, so that's alpha of S naught minus r n of S naught. Except that's a plus because okay, fine, I distributed the minus. This is supposed to be plus right here. There's 3 places I needed to change the sign. I changed it in 2 of the places, but not the third. Curses. All right, great. And so we're supposed to take this and calculate the length squared, right? So here I have said that alpha of S minus C is equal to Rn of S. There's no differentiation needed here. I just need to see through the algebra correctly. What's that? You told me something. What would you tell me? Oh, okay. So C is equal to gamma of S for all S, and I just need to, I'm working too hard down here. I'm working too hard. I just need to write, what is gamma of S equal to? Gamma of S is equal to what? It's actually already like almost apparent here. Gamma of S is equal to, garbage. Sorry. Alpha of S plus R n of S, right? So that says that alpha of S is equal to C, which is a fixed point, minus R times n of S. But anyway, more to the point, that shows that I'm still kind of like, okay, great, that's true, but not really the point. The point is alpha of s minus c is what? It's equal to Rn of s, right? For all s. And that equation shows it's a circle because it shows you that if we calculate this distance, right, it's equal to this. But n is a unit vector, so this is just equal to r. That says that the distance from the center point C, which is a fixed point, and the curve alpha of s, that distance is fixed and is equal to r, which is to say that it's on a circle of radius r. And remember that radius was defined to be 1 over kappa naught at the start of in the earlier part of the proof. Sorry, I made the proof seem about twice as long as it actually is because I got lost in the middle of it. Sorry about that, but anyway. Now there's one other example here, which is example 2.4.7. Example 2.4.7 looks at kind of a similar argument to show that if you have a sphere, right, if you have a curve on a sphere, then the curvature has to be at least as large as the reciprocal of the radius of the radius of the sphere. So like the curves of least curvature on a sphere are the great circles. Any other curve on the sphere has a curvature which is larger than the curvature of the great circles on the sphere. So the proof of that's on page 41 in the notes. I'd encourage you to read it. The method of the proof is almost identical to what we've done in class for the last two proofs, so I won't belabor it. All right, I'll move on here. Now, so everything we've done so far has been for unit speed curves, right? What if the curve doesn't have unit speed? How does that go? So how, oh yeah, thank you. Oh, I'm already there? Oh, thank you. Oh, it was very unsettling when I didn't see you do it. And then like, it's good. So let's see here. If we have alpha of t, right, then you could relate that to like alpha of s of t if you want to abuse notation a bit here. I mean, technically speaking, these are different functions, right? So you should really put like a tilde around one or the other of them, you know, like this one there, whatever. But if you calculate, you know, alpha tilde prime, what do you get? You get alpha prime of s of t, right, times ds dt. So that's the first thing. And if you don't mind, I'm going to drop the tildes, okay? I mean, so here's the deal. T, let's see here. Excuse me. Words. Okay, so definition, if alpha is regular curve, then t, the unit tangent, is defined to be 1 over the magnitude of alpha prime times alpha prime. So, of course, I would remind you, let's talk about some physics notation. You know, physics, we tend to say alpha prime of t is the velocity, right? And the magnitude of the velocity is the speed, right? In fact, given this, I'm going to put a vector on the v to make full contact with physics notation. And physics notation would do what? The speed would just be denoted by just v without the vector, right? That's their typical notation. So in this way of thinking, we have, check it out, the speed v, or excuse me, the velocity v is equal to the speed v times the unit tangent vector. So the unit tangent is the direction of the velocity in the sense of a unit vector being the direction of a vector. All right? So let's see here. But the thing is, this thing I just did, what we have here is, let's see here, t, well, I'm sorry, my mind is not clear on what I want to say here. Let me erase it. I mean, it's not wrong what I wrote, it's just not getting to the point. All right, so getting to the point here, dt, right, for example. If you want to understand, like a quick way to remember the chain rule, it's like this. This is ds dt times dt ds. Now this is an abusive notation because technically t as a function of arc length is not the same as t as a function of time. So really I should have some tildification of this to make it proper, you know, but whatever. The bottom line is that this is v, speed v, times dt ds. You're like, I want another notation for the same thing. Fine, since you asked. S dot times dt ds is another way you could write this. Because S dot is the speed. The time derivative of the arc length is the speed. So, yeah. Now, dt ds is what? So this is v kappa n, right? So if we use a non-arc length parameterization of a curve, we calculate the derivative of the unit tangent with respect to time. The magnitude of, in other words, the theorem is this. The magnitude of dt dt is equal to the speed times the arc length, right? Or another way you could say it, aka to calculate the curvature rather, with respect to a non-unit speed curve, you can calculate the magnitude of the derivative of the unit tangent and divide by the speed. Similarly, if you look at dB dt, well, that's equal to ds dt dB ds, but dB ds is minus tau n, right? So you get minus v tau n, and this gives us the theorem that the torsion as a function of time, you do 1 over the speed, minus 1 over the speed times dB dt dotted with n. So in short, if you want to calculate torsion or curvature with respect to a non-unit speed parameterized curve, we have to divide by the speed to be fair. Those 1 over v factors were not present in our original way of thinking because, well, they're 1 for a unit speed curve. And this is a little bit more subtle, but our definition of curvature and torsion was a reasonable one if you think about, there's no parameter dependence except for the trivial one in terms of like where you start the arc length being 0. Arc length is a unique parameterization, geometric parameterization for a given curve once you pick a starting point. If we use time to define these things, well, there's lots of different time parameterizations of a given path, and our definitions of curvature and torsion would be on, you know, shaky ground if we'd made them in terms of time, but we didn't. We made them in terms of arc length. And now I'm just showing you how to translate it into a calculation with time. Yeah. So in short, if you change these from S's to T's, what happens? Am I right? I can't. Yeah, good. So if I want to erase this and this and this to be T, I have to put V, 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 and V. That's what happens. Now, I think it's a lot of fun just to take a second and take a little bit longer look at physics. In particular, motion in 3 dimensions, right? So let's see here. We have, so let's talk about kinematics, basically. So first of all, we have, alpha of t. That's just the position, right? Position at time t. We differentiate, what do we get? V vector d alpha dt, that's the velocity, right? But we also know that in terms of the Frenet-Serret apparatus, we can write the velocity as what? The speed times the unit tangent, right? And furthermore, acceleration, right? That's dv dt. But what else is it? It's ddt of the speed times the unit tangent, right? Now, generally, the speed and the unit tangent are both functions of time. So when I differentiate them, I have to do the product rule. And the product rule gives me little dv dt times t plus v times dt dt. Now, this guy right here, you could also express as s double dot. It's the second time derivative of the arc length function as a function of time. But in contrast, the dt dt, well, that we can use the Frenet-Serret equation to write in terms of curvature. See, that's kappa n, well, kappa vn, because we're time parameterization. So what we got here is we got dv dt times t plus vv, which is v squared kappa n. And there you go, that's the formula for the acceleration in terms of the Frenet-Serret apparatus. You should recognize there's 2 components to the acceleration, right? There is a what? A tangential and a normal. There's no binormal. The acceleration doesn't have a binormal component. But and if the speed is constant, there's no tangential component, right? But what is this over here? Can you guys recognize this, what this is? The what? It's okay. So if we're going in a circle, right, then this is more familiar because then, if the acceleration is like this, you break it into 2 pieces, right? You've got the tangential part of the acceleration, which is, well, dv dt t, and then you've got this piece right here, which is the normal part of the acceleration. But if it's going in a circle, by the theorem I just erased, curvature is 1 over the radius. I mean, that's not quite that's the opposite of the theorem. That's the converse of the theorem, isn't it? But anyway, it is true. If you fit a little circle, the reciprocal of that radius, the reciprocal of the radius of the osculating circle is what it's following, and that gives you the so-called normal component of the acceleration. you recognize the formula for centripetal acceleration, v squared over r. V squared over r. And now it's starting to be more familiar. Yep, yep. Now, Now, what's fun here is to just keep going down this path. And this isn't even in my notes, but I thought it would be fun. Take one more derivative, right? So the jerk is the derivative of the acceleration. I don't know if you guys knew that or not, but it's true. And so if whew, that's a lot to differentiate, isn't it? Like there's, well, let's just say here there's the d squared v dt squared t plus dv dt t prime, right? Plus the derivative with respect to t, I'll just write it as v squared kappa n plus v squared kappa n prime. Now, t prime just gives you a normal component, right? This is just normal. In summary, guys, this here, there's no b. There's no binormal part to that piece, right? And this over here, that has a partly binormal piece. If you look at the Frenet-Serret equation, there's only one piece which is coming from the binormal, this piece over here, right? So the binormal piece of the jerk, you can see from this equation I have above that j dot b, all right, j dot b is equal to v squared kappa n prime, but the n prime, the piece that matters to the dot b, it's just this piece. So we get tau v from that. So v cubed, I believe. V cubed kappa tau. That's the binormal component of the jerk. Fun fact. So in other words, alpha prime 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 dot b is equal to that. It is what it sounds like. So the jerk tells you when the acceleration's changing, and that's actually what we kind of more experience if you're on a race car track or something, or you're on like a train track that's got a straight section and then a curved section, and you go from that straight to that curved section, all of a sudden you'll feel this. Yeah, that's where the jerk is non-zero, because you're changing the acceleration a lot. I mean, the jerk is largest there, but we don't talk about it in physics much. But it probably has the answer to more of the questions of like, why don't I feel that more? I mean, like I think it may answer questions of feeling more effectively than acceleration in certain regard. Now I think if you take a step back and look at everything that we've done so far, you'll realize that to actually calculate Tn and B, curvature and torsion for a curve, it's quite horrible, right? I mean, it's pretty bad unless we have a relatively nice curve. Now, I have some super sneaky trick formulas. In theorem 2.41, I noticed something today, so it's kind of a fun little thing. One of the formulas here, I don't know if I fixed it or not, but the formula is supposed to be that the torsion is equal to alpha prime cross alpha prime prime dotted with alpha prime 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 divided by the length of alpha prime cross alpha prime prime squared, right? And the thing I was noticing there's more, that theorem has more than just that. I'm just going to focus on this one because I have a slight proof of it to give with you, to share with you. And here it is. So like alpha prime cross alpha prime prime, what's that? Well, that's nothing more than the speed times the unit tangent crossed with what? Alpha prime prime is, well, that's v t plus kappa. And we just have this right there, kappa v squared, right? And so the t cross t term, that doesn't matter. T cross t is 0. But what we have is alpha prime cross alpha prime prime is, what's t cross n? T cross n is b. So this is kappa v cubed b. So when we take alpha prime cross alpha prime prime dot with the jerk, the only thing that matters is the b component. Kappa v cubed times, I'll write it out, v cubed kappa torsion. But on the other hand, the length of alpha prime cross alpha prime prime is what? The length squared. That's kappa squared v to the 6th.
Yeah, I was about to say whatever cancels out.
And when you divide those, the v to the 6th cancels, the kappa squared cancels, and you're left with tau. And that's why that formula is true. Anyway, whatever O'Neill has on page 72, 73, it's probably more clever than that, but anyway, proof. And then finally, let me just rattle off some results here at the end of the section. So these are things that we can prove. Curvature is 0 if and only if the curve, so this is for a, my preamble to the theorem says let alpha be a non-linear regular smooth curve. Item number 1 in the theorem, kappa is equal to 0 if and only if the curve is part of a straight line. Dude, really? So, come on. Like maybe that item number 1 has to be a pre-theorem to this theorem or something. Anyway, my organizational skills here lacking a little bit, right? Anyway, item number 2. The torsion is 0 if and only if the curve is a planar curve. We proved that today. If the curvature is greater than 0, if it's constant, and the torsion is equal to 0, the curve is part of a circle. Proved that today. If the curvature is positive and the torsion is positive, and they're both constant, all right? That's true if and only if the curve is part of a circular helix. We saw one direction of that proof today with our helix example. We proved that the torsion and curvature of a helix, a circular helix, is in fact, they're both constant. And then item 5, the ratio of the torsion to the curvature is non-zero and constant if and only if the curve is part of a cylindrical helix. Do you guys know what a cylindrical helix is? Like it's a helix which is formed by wrapping a curve around a cylinder, right? But isn't that what a helix is? So you're like, well, see, that's because our usual use of the word cylinder is not as general as the word cylinder means. Like a cylinder it can be just formed by any closed curve stacked on top of it. So you can have like elliptical cylinders. Like, every one of these being an ellipse, not a circle. It looks like a circle, dang it. Yeah, like, exactly. So, and then if you were to, say, wrap, you wrap a curve around there, and so forth, then the ratio of the torsion to the curvature is non-zero and constant for such a curve. That's another thing that's proved in O'Neill. In fact, O'Neill has much more to say about Frenet curves in a section that I'm essentially skipping because he gets way into the weeds. I mean, you could spend a couple more weeks on that one section, but I'm going to go on in this part, and so we're going to go on and we're going to cover covariant derivatives in the last part of the chapter here. Now, I'm going to take about a 5-minute break, and then we'll dive into the next section, and I'm hoping to finish before 8. So, all All right, whatever time I don't, I will give you 4 hours of lecture in a week. So like if I use up 2.5 hours here, whatever time I have left, I'll try to behave and not give you another 3 hours of videos or something, right? You don't want to hear me talk that long. But anyway, I'll stop it for the moment.